Hey, I'm Kaushik, a backend engineer. I always wonder how YouTube scaled their application to millions of users. So I decided to build my own YouTube. Not the entire YouTube, but the critical piece that kept it alive. This project, Video Pipeline, isn't a toy project. It's a attempt to build a fully distributed parallel video processing and HLS streaming pipeline. It's my attempt to understand what happens behind the scene when you hit the upload button. It was painful while building this project, but good kind of painful. So in this video, I'll walk you through how I built it, why I built it, and the challenges faced during the making of this project. The initial idea of this project wasn't to scale this to this extent. The initial goal was just to see if I could make similar platform to YouTube, how the YouTube handles chunk uploads, how it manages streaming. But later I realized the entire application I built was only for a small user. But scaling this application was difficult because it took a lot of time, a lot of thinking, and a lot of problems or challenges. Uh, Recently, I was learning about microservices, and I decided that I can give an attempt to scale this application. So here is the system design that I came up with, and I have built this system design. YouTube scales because it decomposes the problem. It's not just upload and playback. A video is duplicated in multiple qualities and then converted to HLS format, which is then used for streaming. Because of this, users don't see buffering in their video playback. So how does video upload actually works? So the user requests the backend server with a init API call, which initializes the initial value of the uh, video metadata. So what the video metadata actually consists of? So it consists of title, description, the total chunk. So how many chunks of video are to be sent from the user to the backend, and how many chunks the backend has actually received, and how many chunks are there in the blob. So because of this, we could implement resuming chunks and retrying the chunking logic, because we are sending it synchronously. So using the title, I am currently generating video hash, which would create a unique video hash, which is then used everywhere further in the video, further in the design. So coming back to the design, the backend creates a row. I am using currently two replication servers, only waiting for first replication server to be consistent, and the second replication server can be eventual consistent because it's first one. This could be easily set up in Postgres. So I'll show you the code, how we can achieve this. So this configuration is there in pmaster. When we create a master server, we can configure this in PostgreSQL.config under synchronous standby names. So if we have two replication servers, suppose I have standby 2. So whenever we create a new row, the server only waits for the first replication to happen. It doesn't wait for the second replication. The second replication can happen eventually. But if you write 2, it will wait for second replication. So this way, the replication works in Postgres. So coming back to the design, then the video, when the row gets created in the database, we get the video hash, and then we send the video hash to the user. Using the video hash, user can request send the subsequent chunks of the video to the backend. So each chunk chunk has a unique ID. I have numbered it 1 to 3 in a sequential manner for easier manageability. So the user sends chunk by chunk to the backend, and after sending all the chunks, a finalize API is called. So what happened? There might be a questions that are what happens if a chunk gets failed. So as we are going in synchronous way and we are counting the total chunks and the received chunks, if we see that the received chunks are less than the total, then we continue from the last received chunk. So this could be resumable. Coming back to the design. So what happens when we call the finalize API? When we call the finalize API, the backend checks if the total chunk and the received chunks are same. If it is not same, the last received chunk number is sent to the user, and the user can continue from there. If we receive all the chunk and the total chunk and received chunks are same, then the original video is then uh, created again using the chunks that are stored in Azure Blob, and later the uh, chunks are deleted from the Azure Blob for storage management. Then the backend pushes a message to Kafka queue under the topic video preprocessing. The Kafka consumers compression and virus scan picks up the video preprocessing topic and then start the processes in Celery workflow. For virus scan, I have used Clam AV, and for compression, I went with FFmpeg. Apart from that, if virus scan we found a virus, then the entire process is halted. Also, I have added metadata extraction from the video. If the user sends wrong content in the wrong content in it, and he send other content in the video chunks, we can cross verify using the metadata we extracted from FFmpeg and the data we have in the database. So it can be flagged inconsistent, and then again the entire process will be halted. If everything goes well, another message is sent back to the Kafka queue video under video processing topic. Every time we send a message, we make sure we send video hash and the video path, actual video path in the Azure blob, because we are indexing the entire database rows in with video hash, so the queries are faster. After we send it to video preprocessing, the Kafka consumer consumes this message. So the video transporters and the thumbnail generation consumes video processing, and then assigns a Celery worker or sends a Celery task, and then Celery manages the execution of these messages. So everything is parallel here. So video processing 144p, 360p, 720p, and 1080p are running parallelly. In my system, if I run this parallelly, it consumes a lot of memory and CPU because FFmpeg requires a dedicated core to execute its process. So it is heavy on a single machine, but if we went with multiple machines, because we are using Kafka, we can deploy these Kafka consumers in distributed network or other servers, and we can scale them easily. Suppose we want 1080p to be multiple servers, so we could scale, run multiple consumers and multiple Celery worker pool. So the scaling is not an issue here. Then comes there is a issue I have faced while initially scaling this. Initially, I spin up multiple video transporters. So I wanted video, suppose video processing 144p. I had running two consumers, and I sent two messages video for video processing, but only once one consumer received the message. Later, I found out that Kafka has a unique way of assigning its queue to a consumer. So for every so I had to make partitions. So if I have n consumers, I have to make sure the partitions are more than n. So it gets assigned to the consumer, each consumer separately, and Kafka manages the load balancing itself. So we don't have to specifically add another load balancer for this. So after completion of video transcoding and thumbnail generation, for each resolution, the database is updated with Boolean variables, and these are marked true. And whichever process or Kafka consumer marks the process as done last will create a master M3U8 file. So what is M3U8 file, you might ask? So I'll show you the exact structure of the folder. So the video folder file has a video hash which contains uh, each data of the video. It contains of source MP4, the thumbnail, JPG, and the HLS, which contains master M3U8, which manages the playlist file of all the resolution videos we have. So suppose 1080p has a playlist file which manages which segment uh, is next to be played. So playlist manages which segment are to be played, and the master manages which resolution are to be selected. It consists of auto selection according to user bitrate. Also, user can select which resolution he wants to play. Then coming back to the design, the master playlist is generated, then stored in blob, and then updated to the database. So we can say HLS master URL. It consists of the master playlist a URL, which then can be used by the client or the user to play the video. So coming back to it, so after the generation of master, the video is marked done, and the video is ready to be consumed by the user. Okay, so the entire process is completed, but there is a issue of visibility. How we'll track what is going on in a distributed network? So this is where logging comes in. So for it, I have used well-known tech stack for logging, which is Grafana Loki, and Promptel or Prometheus. For it, what it does is Prometheus or Promptel collects the raw logs from each server. So basically, it gets the logs from API server. It also gets logs from Kafka consumers. It also gets logs from Celery workers, and then processes the log and uh, sorts them by time series. And then the processed log are sent to Grafana Loki. Grafana Loki is a storage, or we can say database for logs, which stores the log and indexes them. So it could be easily queried by the Grafana using logql. And this tech stack actually works with the distributed network because of how Promptel and Grafana Loki collects and indexes the logs, and how Grafana can easily query them on Grafana Loki. Also, we can check the status of each Celery worker using Celery Lava, which shows the uh, current currently which workers are running, currently which tasks are being performed. Okay, so we saw how entire design actually works, how API servers can scale independently, how Celery Celery scales, and how Kafka consumers also scales, also database and blob. Uh, Now coming to the actual application. So this is what my front end looks like. I am using Vanilla.js. Also, let's try uploading a sample video. I have a sample video and I hit upload. So as you can see, there are 9 chunks and each chunk is getting uploaded to the backend, and the backend server gets log. So it received post request. It received 8 chunk. Then it's currently pre-processing it before finalizing the upload. So it's merging it, and then the entire upload has been successful, and a Kafka message, pre-processing message, has been pushed to the Kafka with the video hash 7740 and subsequent, and a Celery task has been assigned, which has started. If we saw the Docker logs, which is video server worker, not this one, worker pre-processing. So as you can see, it is checking for virus scans right now, and coming back to the application design. Currently, it's scanning the virus. This take time, so I'll fast forward the video. Okay, so now the compression of the video has actually started using FFmpeg. Okay, so now the compression has been successful, and the video is then uploaded back to the blob. And after uploading, a new Kafka message is then pushed to the server, as you can see. Okay. So Kafka message video processing has been pushed with the message of the current video. So we can see the current video hash and currently which consumers are active. This is Kafka UI. So these are the consumers currently available, which are consuming the Kafka messages. Going to Flower, we can see the thumbnail generation has failed. So using video task run Python hash, the Celery task was failed again and again because the processing power needed to execute the FFmpeg command wasn't sufficient, and, and after I stopped all the background processes and other tasks and ran the program again by just producing a message here for the video processing, and the video processing was successful, and the master playlist was generated, and the status of the video was updated from processing to ready to watch. After that, if we see the loading bar, as the quality is set to auto, the video quality is determined by the master playlist according to our network bandwidth. So if we play the video quality seems to be at highest resolution. But if we go to 144p, the resolution suddenly drops drastically. If we say the next chunk aren't getting loaded with the highest resolution. But again, if we switch back to 1080p, the next subsequent chunk are again fetched by the master playlist, and then we get the 1080p resolution chunks or segments. Before I wrap this up, the design you saw previously wasn't the first design. The current design you see was the initial design that I made. This was simple, but this wasn't scalable. Initially, I didn't have Kafka queue here. I simply had a database. So I added every row for new messages with the status and the timestamp as well as video hash, and then index created a composite index on three of them. This worked, but uh, if we scale the application, having thousands of workers, this application soon starts to break because multiple multiple consumers are racing to get the latest row and trying to log. If we implement Even if we implement a row level log, the race condition wasn't avoidable, and the overhead of managing the log was massive. The memory usage would spike, in turn resulting in slower query performance, inconsistent data, and duplicate transcoding or duplicate processing. So this wasn't the ideal approach. So I went with using Kafka, a fan out approach or pub sub approach. Kafka managed the load balancing between the consumer itself, so I didn't had the overhead to manage which consumer consumes the message and how it is uh, load how it can scale. Because if I want to scale Kafka, I could create multiple partitions in it and add multiple topics if I had to. So this approach was what I went with because of its scalability and simplicity. There's one more thing we should talk about, a design choice that was an option, but I didn't go with it. It was practical. I didn't process the video in chunks, not because chunk transporting is bad. Actually, it's how real production pipeline works, splitting the video into small parts, processing them in parallel, and merging them back. It's faster, it's cleaner, and more scalable. But here's the truth. Chunk transcoding needs serious compute power. Multiple FFmpeg workers running per chunk, dozens of parallel jobs, the memory spikes, and the system throttles. I tested it. My system couldn't handle it. I was burning cycles, throttling core, and the whole machine started choking. So I made a decision. Process the entire video in one go. Is it slow? You might ask. Yes, but it's the only thing my current hardware would actually work with. If I had a real server cluster, or if this was a production deployment, I would have processed whole video in chunks. I'd split them into segments in parallel independently with chunk level retry, faster, fault tolerant, and cloud friendly. This project isn't missing that because I didn't know how, it's missing it because of hardware reality. Sometimes the limit of the machine you're using determines the architecture you choose, and for this project, whole file processing was the only viable option. Now, one more thing that you might wonder why this whole system is not right. That is because the compute power required to deploy this system is massive. Multiple FFmpeg workers, Kafka, Redis, database, FastAPI, API service, Azure Blob Service. the costings are massive. To deploy this entire application, I would need a cluster of machines or high-cost cloud setup. Uh, uh, that is not possible for me right now. But you can try the code out. I have linked the GitHub repo in the description. Also, if you are watching this video this far, thank you. Any feedback you have, any improvement or different approach, I would love to hear. So comment down below. Play with the code, break it, modify it. That's the whole point. This was Video Pipeline. I am Kaushik, and thank you.